Okay, so we have a question here. It's question 9. It's taken from Physical Sciences. Paper 1, still for grade 11. This question is on electromagnetism, right? Cool. So let's just read the question statement quickly. It says to us an induction coil with an area of 48.6 square centimeter and 200 windings is rotated clockwise. So you can see that this thing, there's your coil, the circle, the round thing, and it's rotated clockwise at in a constant magnetic field, and the value of that magnetic field is 2.4 teslas, right? So what do you notice, that this your coil is placed between magnets, right? Two magnets, north pole, south pole, and we know that electric field lines always emerge from the north pole and point towards the south pole, right? So that's why it experiences that magnetic field there, and it's constant, right? Cool. And now we say the question continues and says that now they give us a graph, and the graph actually shows the induced EMF as it varies or as it changes with the inverse of time, right? Cool. So what does that mean? This means that on the y-axis you have your EMF, which is measured in volts, and then on your x-axis you have your time. They didn't give the units there, so I'm assuming we'll say it's given in per second, right? Because it's the inverse, it's 1 over the change in time, right? Cool. So you see that this is a straight line, and because I'm not going to bring up this question again so that you can see, just look, I want you to look at this, because this is the value we're going to use to answer question 9.2. So you will say, okay, if my EMF here it's at 3, right? It's 3 volts. How much is my 1 over change in t? So 1 over change in t, if you look carefully, if you go down, is around about 1.8, right? So remember those two values. And then we are asked to give to state Faraday's law in words, and this is a definition that you should know. It's a standard definition. You can find it in your book. You can find it in most physical sciences learning materials. And Faraday's law in words says that the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux linkage with the conductor, right? But we'll explain that a bit more later on. And then, like I mentioned, 9.2 says use the information in the graph to calculate the change in magnetic flux. It's 5 marks. And then the coil rotates through an angle theta, right? So this is the initial position it's at, to a position where the magnetic flux becomes 0. And now we have to calculate what that angle theta is, right? Cool. And that is just 4 marks, right? So let us try to actually answer this question. So it wasn't a long question. We have already answered question 9.1, and that question wanted us to state Faraday's law in words, right? And we said that Faraday's law says that the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux linkage with the conductor, right? So you have to be able to know the definition. It's a standard definition. It's available in your textbook. Then question 9.2 wanted us to use the information. So we were given a graph, and on that graph, it's a graph. On this axis you have E measured in volts, and then on the x-axis you have a 1 over a change in t, right? So that is the graph that is given to us, and it was a sort of a straight line. So if you now go so we have to use the information. So we selected a point on the y-axis. The point was 3, and it coincided with 1.8 on the x-axis. So that was the point that I chose, right? Cool. And we have to use this information here to find the change in magnetic flux. So Faraday's law, in symbols, if you write it in symbols, basically says that your EMF there is like this. So this is the change in magnetic flux. So this is an equation you should be familiar with, right? Cool. So N is the number of windings, right? Which was already given to us. And then change in this Greek letter phi or phi is your magnetic flux, right? And then a change in t is your time, and this is the EMF. So what are you noticing in this instant? You know what the EMF is for that point, so we chose 3. No, that's the, if I'm writing the coordinates, is 1.8 and 3. So this will be my 1 over change in t, and then this will be my EMF, right? Cool. So I have the EMF. I have 1 over t, because I want you to notice you can write this. So change in magnetic flux multiply by 1 over t. This is the same thing. So I already have 1 over t, which is 1.8. I have n, which is the number of windings. It was given to us in the question statement. So now you realize it's just a matter of rearranging and making the change in magnetic flux my subject, right? So let us try to do that. So our EMF in this instant is 3 because we chose that point 3. Somebody else could have chosen a different point. You still get the same answer, right? So you have 3 equals to the negative of n. Big letter N is my windings. It was given to me as 200. I apologize for that, right? And then multiply by, and then 1 over t is just 1.8 multiply by 1.8, right? Am I missing something? I don't think so. So you have 200 multiplied by 1.8 multiplied by your change in magnetic flux. So this is your magnetic flux. So 3, so minus 200 multiplied by 1.8 is going to give me a value of about, let me just do it quickly. So it's going to give me a value of about negative 360. Then we have your change in magnetic flux, right? I want to be left on the side of the change in magnetic flux. I simply just divide both sides by the negative 360, right? So these two will cancel, and then you have your change in magnetic flux, which is 3 over 360, and it's supposed to give you a negative of 0.0083. So magnetic flux, the change in magnetic flux is measured in Webers, so you just write WB over there, and that's your answer. Quite straightforward if you think about it. And now the question continues to say that the coil is rotated at an angle theta to a position where the magnetic flux becomes 0. So I'm going to try to draw, or actually illustrate what is it that they are referring to. So remember, initially you have your north, or no, your south pole. There's your north pole, and we said those lines will always emerge from north pointing south, your magnetic field lines, right? Inside this magnetic field, you have a coil. So it's a round coil, and it's rotating, right? It's rotated from and when it makes an angle theta up until let's see what the question says. So it's rotated through an angle theta to a position where the magnetic flux becomes 0, right? So your point is your thing is rotated up until it makes where the magnetic flux is 0. But now, when does the magnetic flux becomes 0? To answer this question, we have to first look at the formula for magnetic flux. So there's a formula for magnetic flux that I'm sure you're familiar with, right? And it says to us that the magnetic flux equals to the product of my magnetic field with the area, all of it, cos multiplied by cos of theta, right? This theta here, it's very important. This theta here is the angle between my magnetic field lines and the normal to my conductor. So remember, the normal line is the perpendicular line. Let me just cover this. The normal line, when we say something is normal, it means that that film has a 90-degree angle with whatever surface, right? So if this is my coil, right, the normal to the coil will be pointing in this direction, so that the angle between this and this is 90, so it's normal. So even when it's rotated, you see, it's still, your normal is still in this way. If it's your normal, if it's rotated this way, this is your normal. It's still maintaining that 90-degree, because what are you realizing is that, if I'm showing you something a bit larger, I can't find anything large. So you just have to, so let's say this was your coil, and then this is your normal to your coil. So the angle between them is 90-degree. The angle between them, this one is in this way and this one is pointing in this direction. So the angle between them is 90, right? Cool. So that's the thing you have to understand, that theta is the angle between this normal to my conductor coil, as well as and the magnetic field lines. So where are your magnetic field lines pointing? They are pointing in this direction, right? They are pointing in this direction. And then you have your coil, your conductor coil rotating. So initially it's shown through a position where it's lying like this. But remember, you're looking at it from this side. That's the side that you're looking at. And then it's like this. It rotates from this position, so that's your normal, to a position where the magnetic flux is 0. When is the magnetic flux 0? So I want you to remember now, it's 0 when theta is 90 degrees, because the cos of theta, because the cos of 90 will give me 0. So if theta is 0, is 90, the cos of 90 will give me 0. It means this entire thing will be 0. So what does that mean? The cos, so that angle between my magnetic field lines as well as my coil, the angle it makes, because as well as the normal to my coil, so the angle between them is 90. When that angle is 90, it means when it's seated in this position, that's when your magnetic flux is 0, and this is its final position, right? Cool. So initially, so to find this angle theta, we have to say, okay, let us say the change in theta, no, I keep saying theta, the change in phi, the change in magnetic flux is given by the final magnetic flux, right, minus the initial magnetic flux, right? And then we say that thing is just given by BA cos theta minus BA cos theta. So initially, this your coil is at an angle theta that we don't know, but at the final position is at an angle in which the normal to the coil makes a 90-degree angle with the magnetic field lines. Remember, theta is that angle between the normal to your conductor or your coil that is in your magnetic field, as well as the magnetic field lines, right? When they make that 90-degree angle. So you'll say, okay, so BA we already know. So what is my B? I'm given my B in Teslas, so it's 2.4. That's my magnetic field. What's your area? So remember, your area is actually given as 48.6 squared centimeters, right? But we have to convert it first to square meters. To do that, you simply say centi just means multiply by 10 to the -2. So remember, everything will be inside the this bracket over there. So you have 4.86 multiply this. If you multiply them out, you just get 10 to the power of -4 meters squared. So you multiply each thing. So 2 multiplied by -2 will give me -4. This thing twice of this will give me meter squared, right? So that this is your area actually in meter squared, right? So I can just write it there and say it's 48.6 multiplied by 10 to the power of -4, right? And then my cos, I'm just gonna continue this on the other line. Cos is 90 minus the same thing is still 2.4, 48.6 multiplied by 10 to the power of -4, cos of theta. Remember, we're looking for that theta, right? Cool. So we have already calculated the change in magnetic flux, right? And we said it's -0.008 Webers, right? And now there you are. This entire thing here, 2.4 multiplied by 48.6 multiplied by 10 to the power of -4, cos of 90 will just give me 0 minus, you can put it in your calculator, but you should know instinctively that the cos of 90 is 0, right? And then you have your values over here. So if you multiply the negative of 2.4 by 48.6 multiplied by 10 to the power of -4, you're actually gonna get a value of 0.011664, right? But then you know that this is also multiplied to the, let me actually do this so that it's clear. So 0. Cos of theta, right? Cool. So you find that on this side you have negative 0.0083. This you don't need to include now. And then you have negative of 0.011664 cos theta, right? Simply divide both sides by negative 0.011664 so that you can be left with cos theta, right? Right? So now this will mean that your cos theta will actually be equals to negative 0.0083 divided by 0.0116664, right? So always check the answers with me, right? And then to find theta, we just take the arc cos. So you just say cos there to the power of -1. You put this entire thing in your calculator. Negative 0.0116664. So this is your arc cos, right? And then you just press your shift and then press the cos button on the cosine button on your calculator. In the bracket you'll put this value and you'll actually come to a value of about 44.64. So that means that the angle that we're looking for is actually 44.64. I hope that was clear. I hope you were able to essentially follow with my logic in terms of understanding how do we go about determining this angle, right? Cool. So actually we are actually done with the question.